We have the two arrays. Now let's build the operations that work on them. Make, set, find, and union. Before any groups are joined, every element sits alone. Each one is its own group and its own representative. Slot 0 holds 0. Element 0 is its own parent. Slot 1 holds 1. Element 1 is its own parent too. Slot 2 holds 2. The same pattern runs all the way across. Every index points to itself. That gives us n singleton trees, each with height 0. Now the code. The function makeSet takes the parent array, the rank array, and the count in. It loops over every index I, from 0 up to n. It sets parent at I to I, so each element becomes its own root. It sets rank at I to 0. A lone node has rank 0. Setting up all n elements costs big O of n, that is 2 constant time writes per element. First, a warning. You might think find of 4 is one hop, just read parent at 4, but parent at 4 may have its own parent. Find keeps climbing until a node points to itself. The answer is the root, not the first parent. Let's watch the walk. We start at 4. Parent at 4 is 3. 3 is not a root, so we keep climbing. Now we are at 3. Parent at 3 is 2. 2 is not a root, so we keep climbing. Now we are at 2. Parent at 2 is 1. 1 is not a root, so we keep climbing. Now we are at 1. Parent at 1 is 0, so we step to 0 and check whether it is a root. Now we are at 0. Parent at 0 is 0. It points to itself, so this is the root. Find of 4 is 0. That took 4 hops. Now the same walk written as pseudocode, and it adds one powerful trick called path compression. The function findSet takes x if x is not equal to parent at x, then x is not its own root. So it calls findSet again on parent at x, and stores the result back into parent at x, then it returns parent at x. That storeback is path compression. As the recursion unwinds, every node it passed gets repointed straight at the root it just found. Because compression is the real lesson here, we show it first in pseudocode, and then in C on the next slide. The C code maps one-to-one onto the pseudocode we just read. The function findSet takes the parent array and x. If parent at x is not equal to x, then x is not the root yet. It sets parent at x to findSet of the parent array and parent at x. This recursive call walks up to the root, and the storeback does the path compression. It returns parent at x, which now holds the root. One find costs big O of height, that is 1 step per level up to the root. Path compression coming next is what keeps that height small. Find with path compression is the main operation of this chapter. Let's see it at 3 levels of detail. This table has 3 columns. The concept, the pseudocode line, and the C1 mechanism, shown 3 ways. The concept: walk up to the root, then repoint every node you pass straight at that root. The next find through any of them is then just one hop. The pseudocode names the one recursive line that does it. Parent at x equals findSet of parent at x. The C is the very same line. Parent at x equals findSet of the parent array and parent at x. So the concept says what happens to the whole path. The pseudocode names the single line. The C shows it in memory, an ordinary array write, once per node on the path. This is the same tall chain from the walk trace. We are about to flatten it with one call to find a 4. Slot 0 is the root. It holds 0. Slot 4 holds 3. So 4 points to 3, 3 points to 2, 2 points to 1, and 1 points to 0. 4 hops to the root. Slot 3 holds 2, which shows the middle of the chain. Each node knows only its own parent, not the root. The picture shows the same chain. 4 sits at the bottom and 0, the root, sits at the top. The height is 4. Every future find through 1, 2, 3, or 4 would cost 1 to 4 hops. Here is the same tall chain. We call find of 4. First we walk up to the root, which is 0. Now watch us push each node down to 0, one at a time. First we push 2 down. We set parent at 2 to 0. In the array, slot 2 changes from 1 to 0. In the tree, the old edge from 2 up to 1 fades to a faint ghost, and 2 now points straight at 0. Next we push 3 down. We set parent at 3 to 0. Slot 3 changes from 2 to 0. The old edge from 3 up to 2 fades to a ghost, and 3 now points straight at 0. Now we push 4 down. We set parent at 4 to 0. Slot 4 changes from 3 to 0. The old edge from 4 up to 3 fades to a ghost, and 4 now points straight at 0. Here is the result. The tree is flat. 1, 2, 3, and 4 all hang directly under 0. The height dropped from 4 to 1. The ghosted chain still shows the old shape, so you can see exactly what changed. Every future find is now a single hop. A learning check. In the chain 4 to 3 to 2 to 1 to 0, calling find of 4 runs path compression. Which parent entries change and to what value? Pause and work it out. The answer is that entries 2, 3, and 4 change, and each now stores 0. Parent at 0, which is the root, and parent at 1 were already 0, so they stay the same. The real program prints exactly this before and after. Let's picture union a second way. Think of each group as an island. Every element stands on exactly one island. To join 2 groups, you build a bridge between their islands. The 2 islands fuse into one bigger piece of land. When 2 islands merge, one island's representative becomes the representative of the whole new land mass. There is still just one leader for the joined group. Everyone who was already on either island is now on the same land mass. No element has to move. They just belong to a bigger group now. And you never split a land mass back apart. Bridges only ever join islands together. Union merges groups. It never breaks them up. Your turn. Let's predict before we reveal the answer. Start with 10 singletons made by make set from 0 to 9. Then run 3 unions in order. First union of 1 and 2. Then union of 3 and 4. Then union of 2 and 3. The question is this. Using union by rank, what does find of 4 return? In other words, who is the representative of 4? Take a moment and commit to an answer before you move on. The answer is 1. Let's walk through it. Union of 1 and 2 makes 1 the root of the group with 1 and 2. Their ranks were equal, so 1 stays on top and its rank rises to 1. Union of 3 and 4 makes 3 the root of the group with 3 and 4. Now union of 2 and 3 links the 2 roots. Find of 2 is 1 and find of 3 is 3. Their ranks are equal again, so 1 stays on top and 3 hangs under it. So 4 points to 3 and 3 points to 1. That means find of 4 is 1. The trap is to chase the arguments and guess 2, but union links roots and find walks all the way up. To merge 2 groups, first find both roots. Then link the shorter tree under the taller tree's root. This keeps the height low. It stops the tree from growing taller just by chance. Watch out for one thing. You may think union of x and y just sets parent at x to y, but x and y may not be roots. Union links root to root, never the two arguments directly. Linking non-roots would tear an existing group in two. Here is the before picture. Root 0 has rank 1 with 2 children hanging under it, and 3 is a singleton root with rank 0. And here is after union of 0 and 3. 3 attaches directly under 0 because 0's tree is the taller one. Notice 0's rank is unchanged. Attaching a shorter tree under a taller one does not make the taller one any taller. That is exactly why the rule works. Let's write union as pseudocode. This is the two-part form from the CLRS textbook. Union finds both roots. Then a helper called link decides which root stays on top. Union of x and y is short. It calls find set of x to get the first root and find set of y to get the second root. Then it calls link on those two roots. So link always receives real roots, never plain elements. Now look at link. At this point, both x and y are already roots. First, it compares their ranks. If rank at x is less than rank at y, it swaps them so that x is always the taller side. Then it sets parent at y to x, the shorter tree hangs under the taller one. The last step handles a tie. If rank at x is equal to rank at y, the tree just got one level taller, so it increases rank at x by 1. That bumps the upper bound to match the new height. In C, this is the same union, with link folded into one function. Let's read it line by line. The function is called union sets. It takes the parent array, the rank array, and the two elements x and y that we want to join. First, we get the root of x we call find set on x and store it in Rx. Then we get the root of y we call find set on y and store it in R. Next, we check the two roots. If Rx is equal to Ry, the elements are already in the same set, so we return and do nothing. Now we compare ranks. If rank at R, x is less than rank at Ry, then y is the taller root. We want Rx to be the taller one, so we get ready to swap. This line swaps Rx and Ry after the swap. X is always the taller or equal root. Now the actual merge happens. We set parent at Ry to Rx, the shorter tree now hangs under the taller root. Then we check for a tie. If rank at R, x is equal to rank at Ry, joining them can push the height up by 1. So in that case, we increase rank at Rx by 1. Rank is our upper bound on height, so we bump the bound, not a measured height. What does union cost? The time is big O of height. Almost all of it comes from the two find set calls. The link step itself is just big O of 1. A learning check on that code. Suppose union were written as parent at a equals b, directly, skipping both find calls. Starting from the group 1, 2, 3 with root 1 and the group 4, 5 with root 4, what does union of 2 and 4 corrupt? Pause and think. Here is the answer. It makes 2 point at 4, but 2 was not a root. 1 and 3 still point at 1, which is now disconnected from 4's tree. So the forest shows 2, 4, and 5 as one group, while 1 and 3 are wrongly left in a separate, disconnected group. The fix is always to union the roots, union of find of A and find of B. Let's run the code and watch what it prints. This is the main part of dsu.c. First, we call makeSet with 10. This gives us 10 singletons, the numbers 0 through 9, each in its own group. Then we print how many components there are. Right now, the answer is the starting count. Then union of 1 and 2 joins those two into one group. Then union of 2 and 3 adds 3 to the same group. Now 1, 2, and 3 are together. Now we print find of 3. This asks for the representative of 3. Next, union of 4 and 5 joins those two into a new group. Union of 6 and 7 starts another group. Union of 7 and 8 adds 8 to it, so 6, 7, and 8 are one group now. Union of 0 and 9 joins those two into a final group. At the end, we print count components again. This counts how many separate groups are left. Now the output. Right after make set, there are 10 components. Every element is still on its own. After union of 1 and 2, and union of 2 and 3, find of 3 is 1. So 1 is the representative of that whole group. After all 6 unions, there are 4 components left. 10 singletons collapsed into 4 groups, 1, 2, 3, 4, 5, 6, 7, 8, and 0, 9.